So question 30, we're getting into some of the distributions of what we call the bell-shaped curve. So in working with the bell-shaped curve, we have the ability to standardize everything. So let's look at this question right here. A certain brand of automobile tire has a mean life of 33,000 miles. That's not very much. And a standard deviation of 2,350 miles. Assume the lifespans of the tires have a bell-shaped distribution. So we'll call this normal distribution later on, but the bell shape is what we have this word right now. So part A says the lifespans of three randomly selected tires were 35,000, 37,000, and 32,000 miles. So find the z-score that corresponds to the lifespan. So again, in working with z-scores, we're talking about standardizing stuff. So when I standardize it, the mean actually turns into zero. And then if we move one to the right, that's one standard deviation, two standard deviations, and three standard deviations. We can have a negative one standard deviations, negative two standard deviations, negative three standard deviations. So we can kind of create this bell-shaped curve here. Again, I'm horrible at doing this, but forgive me here. But remember, one standard deviation, we have basically 68% of our data is in this range. Two standard deviations, I think it's like 95% of the data is between two standard deviations. And then three standard deviations, you have, I think it's like 99.7% of the data is within three standard deviations of the mean. So z-scores can help us what we call standardized stuff. So to create a z-score, and then like I said before, this would all be in tables. But right now, and later on, I'll show you how this goes in a calculator as well. So to find a z-score, we need to know the data entry minus the mean divided by the standard deviation. So we have a tire that was 35,000 miles. So if we go 35,000, if we subtract the mean, which was 33,000, then if we divide it by the standard deviation of 2,350, that will convert the score into what's called a z-score or a standardized score. So if we have 35,000 minus 33,000, that's going to be 2,000. Then if we divide that by the standard deviation of 2,350, that'll turn that into a z-score of, and if we round to the hundredths place, that's going to be 0.85. So 0.85 would be about here, approximation. So it's not quite one standard deviation from the mean. So a 37,000 mile tire, if we subtract that from the mean and divide that by the standard deviation, that'll give us generate a z-score. So 37,000 minus 73,000 would be what? 4,000? So 4,000, if I divide that by then 2,350, that'll give me a z-score of like 1.70. So that z-score would be 1.70. So 1.70 would put us about here. Not quite two standard deviations from the mean. So the next one was a 32,000 mile tire. So 32,000 minus 33,000. Then if I divide that by 2,350, notice here we're actually going to get a negative z-score because we didn't quite make it to 33,000 miles. So notice that 32,000 subtract 33,000 actually gives me a negative 1,000. Then if we divide that by 2,350, that'll turn that into a z-score of negative 0.43. So negative 0.43. So negative 0.43 would be around that area there. So not too far off from the mean. So those would be converting all of this into what we call z-scores, which kind of standardizes it. And then, like I said, back to my time, it would be in a table, but now we'll have technology to generate all this. So what we pick up on is, according to the z-scores, would the lifespans of any of these tires be unusual? To be unusual, you have to be out past two standard deviations. So notice that none of the scores went out past a -2 or a +2. All the z-scores stayed within two standard deviations of the mean. So at this point, this is all considered nothing unusual because nothing is out past two standard deviations. So as we move forward, you'll see me draw more and more of these shapes to kind of help understand the data. So the lifespan of any of these tires was not anything that was not expected. Now, part B gets into then the lifespans of three randomly selected tires are 30,650, 35,350 miles, and 33,000 miles. Use the empiric rule and find the percentile that corresponds to each lifespan. So remember, we have the 68%, 95%, and 99.7%. So remember, we have our bell-shaped curve that looks like this. So if we kind of draw this out again, forgive my drawing here. So the mean is 33,000. And then our standard deviation was 32,350. So if I have this 33,000, let me clear this off here. So if I have 33,000 and if I add 2,350, that's going to be one standard deviation for the mean. So 35,530 would be one standard deviation from the mean. If I add 2,350 to that, that's now going to be 37,700. That's going to be two standard deviations from the mean. Then if I go three standard deviations, if I add another 2,350, that's going to be 40,050. So 40,050. So notice that if we go out past 33,700, we're going to get into an unusual event here. So if I go the other way, so if I have this 33,000, if I subtract 2,350, that's going to give me 30,650. That's going to be one standard deviation from the mean. If I subtract another 2,350, that's going to create 28,300. 28,300 would be two standard deviations from the mean. And then if I subtract another 2,350, that's going to give me 25,150. Now, notice how they said this is bell-shaped. So one standard deviation. So I have my data is going to come up. It's going to go from increasing, it's going to turn and start decreasing. So it's going to be decreasing, then it's going to turn and start going out that way. So remember, if we're one standard deviation from the mean, 68% of our data is within one standard deviation of the mean. If we're two standard deviations from the mean, 95% of the data is going to be two standard deviations within the mean. And then if we go out three standard deviations, 99.7% of our data is going to be there. So the first question is this: what's the percentile that corresponds to each lifespan. So if we have a 30,650 mile tire, they want to know the percentile. So 30,650 would be here. Now, percentile, remember it's area, it's going to be the area to the left of this. Because remember, percentile, we had, how do we compare from left to right? So percentile means we're going this area here. So what we need to do is find what the area is under the curve in this spot here. Now remember, 33,000 cuts the graph in half. So at this point, we're at 50,000. Notice that the area between these two was 68%, which means half of 68 is going to be this 34%. So what I pick up on is 50% would be halfway across. And then this region here is 34%. So if I go 50 minus 34, it's going to give me 16%. So this percentile for the 30,650 would be 16%. So, so what does that mean? For us, when we talk about percentiles, 30,650 is, it did better than 16% of the tires on the road. So that's not a very good percentile. 16% better than the rest. So the next number they gave us then is this 35,350. This 35,350 would be from here all the way over to here. So percentile wise, we want to find the area from left to right, from here to here. So notice that we're shading over half of it. We've got this half here is 50%. And then we also got this part right here, which is another 34%. Because remember, 68% of the data is within one standard deviation, but notice how that 68% is cut in half, 34 and 34. So that means from here to here is 34. So what we really have is this 50 and this 34. So if I add 50 and 34 this time, that's going to give me my 84%. So if your tire got 35,350 miles, you're in the 84th percentile, which means you outperformed 84% of the tires on the road. 33,000, that puts us right smack in the middle. That's the mean. So you're at 50-50. So 33,000 is at the 50% mark. So you did better than 50% of the tires on the road. So notice that if we went all the way out here to 40,500 or something, notice how we're in a high percentile. So if we got 40,050, we're getting a huge percentile there because we outperformed most of the tires on the road. So that's kind of how we're going to start to be looking at this area under the curve as we move forward, which is going to give us what we call percentiles.